Last week, two interesting developments occurred in the world of electricity transmission. First, Mid-Atlantic grid operator PJM indicated it's now using ambient adjusted ratings to determine how much power can flow through its lines. And second, the U.S. Department of Energy announced it will award billions for quick and effective upgrades to the transmission system. Let's quickly break down the transmission-related challenges and why these announcements matter. First, it takes forever to connect new supply assets to the grid at a time when we badly need them. Although some recent improvements have occurred, the latest December 2025 report from Lawrence Berkeley National Laboratory, with data through the end of 2024, highlighted the issue. For all projects seeking interconnection to the grid from 2008 through 2019, only 19% of the projects actually flowed power by the end of 2024. The typical project built in 2025 took 55 months to get through the queue, compared with 36 months in 2015. So yep, we have a problem there. There's a second challenge. Even if all that new capacity could be processed through the interconnection queues, pretty soon those numerous new projects would run up against physical limitations of the existing transmission system. There are simply not enough lines to accommodate the planned resources, let alone meet projected new demands. And few new lines are being built. Consulting firm Grid Strategies reports that less than 1,000 miles of 345 kilovolt (keV) transmission lines were completed in 2024. Far less expansion than is needed, especially in the face of that enormous data center demand we keep hearing about. A huge part of the problem is the challenge of permitting for new rights-of-way. Try moving power from state A to state B, and the permitting delay can kill you. The 3,500 megawatt SunZia line, for example, from New Mexico to Arizona, that will be commissioned this year, has taken over 17 years to complete and involved 10 federal agencies in the permitting process. The Grain Belt Express from Iowa across Missouri to Illinois and Indiana has also been in the permitting process of a similar duration. No relief is coming anytime soon, though there is a glimmer of hope that the federal government may reform the permitting process prior to the midterms, but don't hold your breath on that one. Fortunately, some relief can be had in the short to medium term in the form of grid-enhancing technologies, or GETs, which let us do more with existing transmission. In addition, there is the growing potential for reconductoring. Let's take these one at a time, starting with GETs. There are a few different technologies here, but the one with perhaps the greatest near-term promise at scale is called dynamic line rating, or DLR. DLR has been around for years in Europe and at a smaller scale here in the US, but hasn't been widely deployed. To understand the promise, it helps to understand the existing limits of the transmission system. As power lines move more juice, they heat up. That's because electrons passing through the lines have to move through the metal atoms that comprise the wire, and they bang into each other, creating heat. The way the physics works is that with a doubling of current, the heat quadruples. If the line gets too hot, it actually physically sags. That's one reason you have to trim trees on transmission lines. To move more current, you can increase the voltage. Power lines are rated by voltage, and the extra high voltage lines are typically rated at 345 kV, 500 kV, and 765 kV. The amount of power moved through these lines is dictated by static ratings, which are based on highly conservative worst-case weather scenarios. For example, static ratings might assume a 100-degree Fahrenheit day with zero wind that could pull heat away from the wire and cool it down. Although these conditions rarely occur, that's what the line is rated at, and flows can't exceed that rating. The reality is that most days, one could move a lot more power through the line if one were not guessing how much one could actually safely move, and you knew instead. So how do DLRs work? Well, using a combination of software and sensors, they first measure ambient temperatures and wind. The latter is an astonishingly effective natural coolant in wicking heat away from the line. Think of the wind chill factor that can kill you in the winter. They also measure how much sunshine is hitting the wire and warming it up. In addition, sensors measure the actual surface temps of the transmission lines. And finally, the technology can employ lasers, GPS, or monitors to determine how much the wire is sagging at any given moment in time. It's kind of like having a real-time MRI on a patient. You don't have to guess what's happening, you know. And that lets you confidently move more power without hitting your so-called thermal violations. How much more? A 2024 case study demonstrated that in the winter, one could exceed static line ratings 100% of the time on a 345 kV line with average capacity increases of 81%. In the summer, one could still exceed the static rating an average of 94% of the time, with average increases across that period of 27%. That still doesn't solve your problem on exceedingly hot and still days, but the rest of the time you could move a lot more power. There's also a somewhat less capital-intensive approach that is an improvement over static ratings, but not quite as precise or expensive as DLRs, since it doesn't require the use of physical sensors, and it's called Ambient Adjusted Ratings, or AARs. With AARs, one uses forecasted weather data with a focus on ambient air temps to automatically predict the transmission line capacity on an hourly basis. So cold fronts bolster anticipated capacity, and heat waves limit it. The approach is an improvement over static ratings, but doesn't account for the cooling power of wind. So while it's less expensive, it only gets you part of the way there that DLRs could offer. The use of AARs was mandated by the Federal Energy Regulatory Commission's Order 881, rolled out in December of 2021, and that set a deadline for this new approach of July of 2025. However, no grid operators have been able to meet this schedule until now, where PJM, just last week, announced that it went live with its AAR. In announcing this accomplishment, PJM noted that it will use hourly ratings from real time to as far as 10 days out. It will also employ monthly seasonal ratings for longer-term studies 12 months out. It remains to be seen how much additional transmission capacity will result, and this is worth watching. Meanwhile, the Department of Energy just announced a funding opportunity worth $1.9 billion to, quote, accelerate urgently needed upgrades to the nation's power grid, unquote. The projects will be selected through the Spark funding program that's meant to develop fast and durable upgrades. Projects submitted have to demonstrate measurable improvements in electric grid capacity and combine physical capacity gains with operational efficiency and/or flexibility. And the DOE specifically calls out reconductoring. That's the process of essentially stringing new and more efficient lines along the same or upgraded poles. With rights-of-way being the single largest limiting factor to growing our domestic transmission capability, it makes sense to fully exploit the ROWs we do have. A seminal 2024 study from the Berkeley Haas School estimated that large-scale reconductoring can cost-effectively double transmission capacity within existing rights-of-way and yield enormous cost savings in the billions. We'll still need to build new transmission, and probably lots of it. But even if Washington finally passes less restrictive permitting laws, it will take many years for these new lines to get built. In the meantime, it's essential to do as much as possible with the infrastructure we have. These two recent developments are a start. Well, thanks for watching, and we'll see you again soon.